Joanna, for the introduction. I'm going to share my screen now. Yesterday it worked, so hopefully
yesterday it worked. Fingers crossed.
So it will work today. Let's see.
That's looking good.
Okay, so now I can go to slideshow. So basically, can you see the first slide?
Yep.
Okay, so apologies again for being late and for having you waiting. Thank you so much for the invitation to present, well, basically what I have been doing for the last 3-4 years. Well, first of all, one question, I still have kind of 45-50 minutes, or I should go quicker or shorten the talk or something like that?
No, I think just say what you were planning to. Yeah, I think if anybody has to slip off, then they will. But I think most of us are free. Yeah, thank you.
Okay, thank you so much. Apologies again. So as you can see by the title of the talk and the introduction that Joanna did, I'm going to talk mainly about the star formation histories. And let's say in the universe, okay? Because I started during my PhD, I was studying galaxies that are really far away from us, from which we can only get integrated information. And little by little, because we wanted to compare different techniques, I was moving to the local universe, and basically I'm mainly working on Gaia data, even though I'm very involved as well in another project that is called Cavity, to analyze and characterize galaxies inhabiting voids, cosmic voids. So the plan was to talk about all these things. As I was preparing the talk and rehearsing yesterday and today, I don't know if I'm going to be able to talk about voids. And now considering as well that I was late and everything, so I will do what I can do. So yeah, basically, I'm going to talk about star formation histories. And the key here is that, well, probably this question is the same question that we all have, which is how galaxies form and evolve. Some of us are interested in the local group, some others in galaxies that are far away from us. Some people work with simulations, with observations, chemistry, dynamics. There are many different ways to try to answer and tackle the same question. So, well, Emery told me that in the audience there will be some students and as well some people that probably are not so familiar with the kind of things that I'm doing. So I'm going to start with a really short introduction, and I don't even know if I should call this an introduction, because you will see that it's very just the outline of what we can do with stellar populations and how we do that. But the idea is that to answer the question of how galaxies form and evolve, in my particular case, I focus on the analysis and the study of stars. Why is that? Well, it's an important component. It's up to 90% of the baryonic mass of a galaxy. And also they are considered fossil records from galaxy formation and evolution, okay? There are some, and now the cat is here as well, so we have the perfect day today. And the other thing is that they can be considered fossil records from galaxy formation and evolution. Some of the stars that we observe nowadays are as old as the universe itself. So basically they have witnessed all these different events. And not only that, the chemical composition of these stars is basically a result of all the events that happened in a galaxy. And astronomy is basically an observational science. So even though there are simulations, there are some theoreticians and so on and so forth, but at least what I do is mainly observational. And if I want to obtain information about the stellar content in a galaxy, the main information that I use for that is basically summarized here. Is core magnitude diagrams and integrated information. If the system is really close to us, we can distinguish individual stars, and then we can get all this information from all the stars belonging to a system and then create core magnitude diagrams. If not, it could be that the unit of information that we use contains information from thousands and even millions of stars all together. This is called integrated information, okay? So in the end, the idea is that what I have been doing, mainly with Gaia and the local group, is comparing color magnitude diagrams with models and with cavity or these void galaxies and galaxies that are really far away from us. What we compare with models as well is integrated information, spectroscopic information, but broadband colors, spectral indices are other things that that can be used. So in order to compare with models, we need to understand the physics behind star formation, stellar evolution, and everything. And one key concept here is the concept of single stellar population, okay, SSPs. The idea is that we kind of divide the problem into populations of stars that has a given age and a given metallicity. The idea is that star formation proceeds in such a way that you don't form just one or two stars. You normally tend to form a lot of stars. All these stars are formed because of the fragmentation of a molecular cloud that is collapsing, and you don't form as many stars of different masses as you want. We see that nature tends to follow what we call initial mass function. So you form more stars of low mass and less stars of high mass. If this depends with redshift, depends with metallicity, with the properties of a galaxy, is another topic that I'm not going to enter. So let's say that this is the case. So when you form stars, you form a lot of them with different masses following an initial mass function. And then, given that we know quite a lot about stellar evolution and that we also have stellar libraries, we have volumetric corrections and everything, all this theory can be translated into the way that we are supposed to observe these stars. And basically, this is what I'm showing here in the case of well, spectroscopic information. Okay, if we start from the top left panel, you have a population, an SSP, a single stellar population that is young and metal poor. And as we are moving to the right or to the bottom, we increase in age and metallicity. And you can see that you move the shape of the continuum from the blue to the red, as well as you start having more and more absorption lines. Apart from that, we can see in the top panel, where we have two lines, one red and one blue, that the luminosity, the amount of light that we receive from different stars depend on the age as well. You can see that a young star is way more luminous than an old star, okay? Because in the bottom panels, everything was kind of in relative units, but if you put it in absolute flux, you have this. And this would be that, like the complete spectroscopic information. We can go to broadband colors, okay, and define different magnitudes and different colors from this spectra, no? From this spectral energy distribution, we can call it, okay. And when you do that, you see that in the end, what you are mimicking observationally is what we call the Hertzsprung-Russell diagram. The Hertzsprung-Russell diagram is temperature and luminosity, temperature in the x-axis, luminosity in the y-axis. But if you go to colors and magnitude, what you have is color in the x-axis and absolute magnitude in the y-axis. So basically, we need absolute magnitude, not only the magnitude. What we see from the stars is the apparent magnitude. We need the distance to transform it to the absolute plane where we can compare with stellar evolution. Because stars don't fall randomly in this diagram, but follow some sequences. We already know that, no? But I think that is a good introduction to what we are going to see later. We see the main sequence, we have the RGB, the red clamp, and in these different regions, we know that stars are going through different processes. It could be that in the nucleus you have the fusion of hydrogen to helium in the case of the main sequence. If you go to the red giant branch, then this fusion is happening in a layer around a helium core, and so on and so forth. I'm not going to enter into many details, But the idea is that knowing stellar evolution, we can create some synthetic CMDs and understand, when you compare with observations, what is the stellar population of the system that we are analyzing. And if here the key thing is the signal to noise, because you can imagine that these are models, so basically everything that you see here, the shape of the continuum and all the ups and downs that form the absorption lines, are information. But if you are some noise, because we are observing the night sky with instruments and we are not free of errors, the important thing here is the signal to noise. In the case of the color magnitude diagram, the important thing is how deep you reach. You can see here, what I'm showing is some schematic representation of color magnitude diagrams of different stellar clusters, okay? And we can see that if we have a very old, a very young cluster, the main sequence turn off, so the moment in which stars leave the main sequence, so they stop burning hydrogen into helium in the core, is located at bright magnitudes. But as we are moving toward globular clusters, for example, this 67, this turn-off is getting fainter and fainter. So the idea is that if we want to reconstruct the star formation history of a system down to all the stages, the beginning of the system, the formation of the system, we need to get as faint as possible, as faint as the oldest main sequence turn-off, basically. Because this is just a composition of several clusters. But you can imagine that when we go to a galaxy, we will have basically this, a mix of stars of many different ages. Okay, so the idea in the end is that we need to compare observations with predictions, basically with models. In the case of the observations, depending on the system, if the system is really close to us, we rely on color magnitude diagrams. If not, full spectral fitting. So basically, we fit this spectroscopic information. There are many other ways to do this kind of thing, okay? But these are the ones that I'm using and the ones that I'm going to show in the rest of the talk, okay? So enough of introduction. So the idea is that we are interested in analyzing galaxy formation and evolution. In my particular case, the way I decided to do it is analyzing stellar content, in particular star formation histories, and depending on the system that I am going to use, that I am going to study, I will use color magnitude diagram fitting or I will use full spectral fitting. So let's start with CMD fitting, that probably is of more interest to this group. And in particular, I will talk about Gaia and our galaxy. As Joanna said, before moving to Gaia, I was working with smash data on the Magellanic Clouds, but I guess that you have heard of that enough from Noelia and Joanna, and also other local group galaxies. But I see that now I'm going to focus on our galaxy and Gaia data. Probably something that I should have done is to define first the star formation history. A star formation history, to me, is not only the rate of formation of stars as a function of time, but also the chemical enrichment, the amount of stars that are born of a given metallicity and a given age in a given moment, okay, in the history of the galaxy. So let's start talking about our galaxy and Gaia data. The key here, the key of color magnitude diagram fitting techniques, is that we compare with models. And to compare with models, we need to be in the absolute plane. And this is the key. If you are analyzing a local group dwarf galaxy, in principle, you can say that all the stars are located at the same distance. Measure that distance with different methods, and that's it. All the stars will be located at the same distance, and then you have the color magnitude diagram in absolute plane, in the absolute plane. In the case of our galaxy, this is not the case. Different stars that we observe in the night sky are located at different distances, and it's important to measure the distance so that we can move to the absolute plane, and we need to measure this distance star by star. And this is something that, well, was done with Hipparcos before, but just in a very limited volume around the sun. The thing is that now we can do it with Gaia for a vast volume around our solar vicinity. Another important thing to say is that indeed star formation histories was a scientific goal, a primary scientific goal of the Gaia mission, as was written in the Gaia Red Book. And it's something that, well, we are doing, and in fact, we think that this is revolutionizing, and in combination with all the advances in all the different fields of galactic archaeology, I think that in the end we will be able to answer this question about how our galaxy formed and evolved. So basically, I'm not going to really talk about Gaia. You already know Gaia, but the key things that are important for me right now for this project is the fact that Gaia is providing colors, magnitudes, and distances, well, parallaxes, but you can transform it to distances for a lot of stars, okay, and covering, as I said before, a vast volume around our sun. And this allows us to move from the apparent plane, where you have some information but you cannot really compare with models to obtain star formation histories, to the absolute plane, where suddenly we can compare apples with apples, and then compare with models and obtain all this information. Okay, so the method itself relies on the fact that, well, I have already said, no, that the position of the stars in a color magnitude diagram depend on stellar evolution. But in this plot, clearly we see how, if we cover the main sequence down to the oldest main sequence turn-off, as I have said before, we can have some, well, a lot of information about the ages. And if you also have information on the red giant branch, you kind of have some this well, this power of discerning between different metallicities. The combination of everything makes us break pretty well the age metallicity degeneracy. But models, because they are models and are coming from theory, are free of errors. But Gaia data, or any data, is not free of errors, completeness, selection effects, and everything. So an important part of the method is to simulate all these uncertainties and all these things in the synthetic CMD. I'm not going to go through all the technical details, because I think that I would like to talk a bit more about the science that we are finding. But basically, the idea is that you create in your computer a synthetic color magnitude diagram without any errors, any completeness effects, and nothing like that. And then what we do with other codes is like mimic as if Gaia observes these synthetic CMDs, and then how Gaia will tell us that those stars look like. And then we will be able to compare models with observations more clearly. And basically we do this with this code that is called DIR-SFH. Okay, this is a new approach that because in the last 3 years and a half or something like that, since basically the last paper in the series, we have been working on updating all the codes, all the steps, testing everything. Well, Joanna knows what I'm talking about testing, but we test a lot of things. And now we are confident of what we are finding, which is basically what I'm going to show you. But the idea is that, no, it's like we have an observed CMD, which is the one that you have on the top left panel, and then we find the combination of SSPs, of single stellar populations, that better reproduce this observed color magnitude diagram. And then by doing this, we get all this information. We get the star formation rate as a function of time. We get the average metallicity as a function of time, but we also get distributions of ages and metallicities of the system that we are studying. So basically we have histograms, distributions of ages, metallicities, and 2D histograms of everything. So it would be like the age metallicity plane, how the age metallicity plane is populated by the sample that we are studying. Okay. Here, in order to kind of test and show the performance of the method, I'm going to compare it with astroseismology. But before doing that, I must say that I mean, this is not a fair comparison. In astroseismology, people are able to measure the ages of individual stars. We are not able to do that. Okay, I don't know one particular star what is the age of that star. But if I analyze a sample, let's say the thick disk, the thin disk, a volume around the sun, I'm able to recover the stellar age distribution, the distribution of stellar ages of that population. It's not the same as knowing the ages of all the stars, but I think that is a point in between that it could be interesting for preparing ourselves for the vast amount of data that we will get in the near future for astroseismology works, because right now we are very limited in that sense by the number of stars that we have that information. So basically what we have done is, considering that the Plato mission will have around 10% uncertainty in the age, what we did was to create some mocks. So basically some burst of populations of given ages, which is here shown in blue. And then what we did was to fit our code to see what we get. And what we get are the red histograms that, if you compare with the orange histograms, are very similar. The difference between the blue and the orange histograms is basically that what we are doing is starting with the input, shuffling the stellar ages according to a 10% uncertainty to see what we get. So we are kind of there in that 10% uncertainty, again, not measuring individual ages, but measuring stellar age distributions. And in what follows, we are going to concentrate on the sphere of 3.5 kiloparsec radius around the sun. Why is that? Because basically we can say that Gaia 5D, and by 5D I mean that I will have information for all the stars of proper motions, distance, and position in the sky, so no radial velocity for the time being. So the 5D sample in this volume and down to the magnitude of interest to us, which is basically around 4.55 absolute magnitude, is complete. So if Gaia is basically complete, no, except scanning laws and some things that have been modeled by the Gaia team and that we can use, then completeness is easier to simulate, and selection effects are not that important. We use parallax offset. We apply the parallax offset. As I said, as distance estimator, we are using the inversion of the parallax, because basically in this volume, it's all right. We don't need to move to more complicated methods. We are able to correct for interstellar extinction, because well, there are some 3D maps and extinction coefficients in the literature that we can use. And also we make some quality cuts in order to have the best sample possible. So very quickly, before I move to the new things, just I would like to review the couple of papers that we already put out using Gaia Data Release 2. In one case, we were focusing on the halo of our galaxy, because it was this controversy that well, when we got the halo of our galaxy that is shown in this plot, we saw this double sequence, one blue sequence, one red sequence, that at the time, quickly, when you put dynamics into play as well, people started to think and to say that the blue sequence corresponded to the last major merger event in our galaxy, Gaia Enceladus sausage, okay? And the red sequence was associated with the thick disk, with the progenitor of our galaxy, no, but mainly with our galaxy, more than with an external origin. But at that point, ages were lacking. There were just a few ages determined using astroseismology, and even though you could say some things, but it was not statistically sound conclusions. So basically what we did was to analyze the color magnitude diagram of the halo, and as I said, what we get from here is the distributions of ages and the distributions of metallicities. So basically, after doing that, if we separate it in blue and red, we see that there is a difference in metallicity. The red sequence was more metal rich than the blue sequence, but in ages, blue and red sequence were basically the same. They were fairly old, which allowed us to kind of close a little bit the debate. And basically the idea is that the progenitor of the Milky Way and Gaia Enceladus kind of formed at the same time. And then around 10 gigayears ago, they merged together, and now everything is phase mixed in the inner halo. The fact that there is a difference in metallicity between Gaia Enceladus and the progenitor of the Milky Way is due to the mass metallicity relation. So basically systems that are more massive in general are more metallic because of the evolution that they have. And the other thing that we did was to compare the star formation, to compute the star formation history of the 2.5 kiloparsec, no, 2 kiloparsec bubble around the sun to get this star formation history. That quickly was a bit surprising because we had this clear burst of star formation. In some other solutions, you can see all these lines are different solutions, and the orange one was kind of the average. In different solutions, we had also different peaks, but the ones that are always in all the solutions are the ones that you can see in orange. And basically what we did is to try to investigate what was causing this burst of star formation. And what we did was to compare with Sagittarius dwarf galaxy, comparing it with the star formation history of the Sagittarius stream, with the star formation history of the Sagittarius core M54, and compare it with what simulations were telling us about the orbital history of Sagittarius around the galaxy. And it seems that this burst of star formation corresponded to pericentric passages of Sagittarius. So we concluded that Sagittarius has also been an important actor in the building up of the Milky Way disk, although some effect from other satellites is something that we cannot discard, probably the Magellanic Cloud in the last billion years or so. And now I'm going to start with new things, okay? So basically all that was done with Gaia DR2 and our previous set of codes. And then we decided to modify everything, to modify the code to create synthetic CMDs. We are using the Basti models. Also, we are using new Basti models that were published by Sebastián Hidalgo some years ago. Previously, we were using an older version. Also, we are comparing with other models, with Parsec, for example. The simulation of errors and completeness is completely new. We started a new code in order to try to simulate all the different things that could have an effect on what we were recovering. And especially we wanted to update the code to compute star formation histories, because there were a couple of things that were kind of an art, because previously we were kind of selecting some bundles in the color magnitude diagram to give more importance to some evolutionary stages to others. Now we are fitting everything kind of, well, not blindly, because there is a reason behind everything, but at least we are not doing all this. So this is one improvement. The other improvement is that before.
Sorry, Thomas, can I just stop you there a second? Sorry, there seems to have an echo seems to have developed in your line. Somebody unmuted themselves.
Bring the participants up and see who else is.
I think it would be someone.
Yeah. Okay. Are we back?
Okay. So now everything is okay.
Yeah, that's good. Yeah, great. Thank you.
Oh, okay, perfect. In fact, I was listening to the echo as well, that it was a bit disturbing, but I said, okay, let's keep going.
Assist anyway. Yeah. No, you're clear as crystal now.
Okay, the other thing that we wanted to improve, because in the previous version we were selecting some H beams and some metallicity beams, and based on that, the solution will work. And basically those beams, it was like making squares or rectangles in the H metallicity plane. So there were some things that we wanted to improve, and we did. We improved them. And after 3 years testing with clusters, with mocks, developing the codes, improving this, improving that, we decided that it was time to check how we did. And to check how we did, the first thing that we said is, okay, let's compare it with the best color magnitude diagram that we can find in the literature, and that is the Gaia catalog of nearby stars, published by the Gaia Collaboration, Smart and Collaborators 20 and 22. Okay, basically this is just the 100 parsec volume around the sun with exquisite distances, basically no photometric errors. So it's, and you can see the color magnitude diagram is here. You can see the white dwarf. You can see the main sequence going down to very, very faint magnitudes, a lot of details. So this is the one that we wanted to use to check everything. This is work that is about to be submitted by Karma. We will present there a lot of tests. I'm not going to show us those tests because it's going to be very, very boring. But one important thing is that even though for our feeds, we always cut at 4.5 around this area, because basically the information that we have here, I mean, you can already see it. Here you have some isochrones of different ages. So in blue is some isochrone that is very, very young, then orange, green, red, and purple. As we are moving older and older, you can see that the main sequence turnoff is getting fainter and fainter. And here in this area, everything overlaps. So suddenly we don't really have information on the age, and it's better to cut here because we maximize the amount of information. But even though we cut here, once that you have the star formation history, the best model, you can extrapolate down to all this area. And this area holds a lot of information about the IMF that we are testing, but also information about the unresolved binaries in Gaia. Gaia is an excellent satellite with an exquisite resolution, but even in that case, we have some stars that cannot be resolved. Okay, some binary stars that are considered one. So basically, what we have done and what we are showing here is to use an isochrone, which is kind of representative of the trend of the main sequence in the Gaia catalog of nearby stars, and plot the difference in magnitude with respect to that isochrone. And this is what we are showing in the black histogram. And then we feed the Gaia, this color magnitude diagram with different recipes for binaries, with different values of Q and different values of beta. Beta is basically the fraction of unresolved binaries that we consider, and Q is the mass fraction that we allow the binary system, the unresolved binary system, to have. And in the end, well, you can see that in some cases there is quite a discrepancy, but in some other cases, in particular the purple one, is fairly similar to what we are observing in the Gaia catalog of nearby stars. So in the end, this is the combination Q01 and beta 30% that we found that it was more similar to reality. And in fact, this value of 30% unresolved binaries agrees with a work by Vasily Beroklov using the Ruwe parameter in Gaia data. Okay. And then here you have the result, no? Because from a technical point of view, this is very interesting, but in the end, we are interested in getting star formation histories. And you can see that, well, the vicinity of the sun is pretty young. Okay, here I'm showing in the x-axis, and I will show a lot of plots similar to this one. The age of the stars, old on the left, young on the right, and then the metallicity on the y-axis. And apart from that, you can see that it's quite bursty. We have a lot of clumps of star formation that we have been testing, and we think that they are to be trusted. So it seems that this is the case. And not only that, we can compare this with other works finding age metallicity relations using astroseismology data, and using as well spectroscopic service, ground-based spectroscopic service. And basically you can see this first positive trend that is seen in these three, and that we see it here as well. I must say that here, in other works, the volume that they are analyzing is pretty large. So when we move to a different volume, we will see this more clearly. This is fairly concentrated to the disk. But then we have this kind of plateau, which we see it here as well. And then this other positive trend that is kind of there with some differences in one and the other that we already see here. So it seems that everything is compatible, but the resolution that we are able to get is quite remarkable. And this was the Gaia catalog of nearby stars. Now, if we move to the solar vicinity in general, what we have done, as other groups are doing as well, is to dissect the vicinity of the sun in different layers above and below the plane in a cylinder. The cylinder will have a radius of around, well, a radius of 1 kiloparsec, and we are moving up to 3.5 kiloparsec above and below the plane. You can see here all the color magnitude diagrams as we move from the disk to the more external part with high values of offset. And we can see that little by little we are moving to have an older population as expected, because we are missing all this bright main sequence. But the important thing is that we want to run our code, because it's not only by eye, we can really get all the information that we want here. So basically now I'm going to show a movie of all these 16 volumes in which we have divided this cylinder. On the top left panel, you will have the color magnitude diagram. On the right top panel, you will have the star formation rate as a function of time. In the bottom left panel, you will have the distribution of stars in space in the set X plane. And the most interesting one, the one that I think that we should concentrate, is the one on the bottom right panel, where we are showing the distribution of stars in the H metallicity plane. And first, I'm going to go quickly through it as if it were a movie, and then I'm going to go back and then little by little explain some of the things that we are seeing. Not all the things, because there are so many things that I don't have time to talk about everything, and some of them we don't really understand what we are seeing yet. So it's things for discussing. So if we start high above the plane, this is what we have, and as we are moving towards the center, we see some consistency and how little by little things are moving until, well, this one, which is the one closest to the disk, that in fact resembles the Gaia catalog of nearby stars. So we can go back again in this kind of movie, and things that we can discuss. Okay, if we are really high above the plane, I must say that here we have clean, so we are removing halo stars. So in principle, this is without halo-like kinematic stars. And basically what we are seeing is kind of the hot thick disk, the splash, no, some kind of the red sequence that we were discussing before. As we are moving towards the center, we suddenly see this kind of three blobs, this one, and this one, that we don't really know, of course, but if you compare with simulations, and there are some works in the literature that have been published recently. It could be a signature of different merging events. The one at 10 gigayears, of course, should be Gaia Enceladus, because this is kind of known. But we have also this bit here, this important bit here, okay, that is dominated in different regions in the galaxy, that we thought it could be Kraken maybe, or it could even be just different pericentric passages of Gaia Enceladus, which would allow us to put some constraints on the orbit of Gaia Enceladus in the same way that we did for Sagittarius in recent mergers. Now we can do it with Gaia Enceladus. Another thing that we can see is this blob, no, several blobs probably related to the incoming of the Helmi streams and Sagittarius. We still see all these bars, but now with this improved methodology, we have more and more detail. Something that is quite interesting is, let me see if here, you can see that little by little a population appears here that is quite stable, old, and relatively metal poor, that when we move really close to the disk tends to disappear. It could be that it's not really disappearing, it could be just the fact that we are more affected by reddening here and the uncertainties is a bit larger. But this could be the metal poor disk and all, no, that some people discuss. So it seems that we see it there as well. There is this interesting gap in star formation as well, that when we have been talking to some simulators, it seems that it makes sense that it could be there. So as you can see, a lot of details that well, it's open for discussion. We can discuss later, and we need to understand what's going on here. And then the next thing that I would like to show is the fact that, okay, we have moved from the best color magnitude diagram that we have moved to this cylinder, and now we can move to the halo. We can move to galactic building blocks. The idea is that according to the hierarchical formation of structures, we think that our galaxy and most of massive galaxies in the universe form via the accretion of dwarf galaxies, of smaller systems. And in fact, we have proof of this in these stellar streams that we see in our galaxy, but that we see as well in external galaxies. And if at the beginning of the talk I was talking about the stellar populations in the sense that, well, they are fossil records and they allow us to unveil the past events in a galaxy, well, if we go to the halo, it's even more true, no? Because in the disk we have the bar, we have the spiral pattern, we have mixing of stars, and we don't have that in the halo, no? Apart from that, it's like we know that all the debris from all this merging is stored in the halo, and we know that the origin of the stars is somehow retained in the stellar motions as well, and they cluster in conserved quantities, as we can see in this seminar work by Amina Helmi and Desiu in more than 20 years ago, in which we can see stars belonging to different satellite galaxies that are disrupted in a galactic potential, how at the beginning they basically occupy a region in integrals of motion, and even after 12 gigayears and after simulating Gaia uncertainties, they are still there. No, it's like they clamp together in integrals of motion. That in fact is what we see. We did this work using early data release 3, because for this we need to have 6D information, so basically not only 5D as we were discussing before with the star formation histories. If we want to go to integrals of motion and the dynamics of these stars, we need radial velocity as well. So proper motions, distance, position in the sky, and radial velocity would be the six dimensions that we need. Okay, so basically this is early DR3. We repeated it with DR3 because with DR3 we have 33 million stars with radial velocities, whereas with early DR3 we only had 7 million or something like that. So basically the statistics improved. We see all this clumsiness, all this Enceladus, Thamnos, Sequoia region, Helmi streams, and many different structures that are summarized basically here. Some of the structures were already known, some others were new. But the key here is that we want to, I was saying that I was going to talk about star formation histories, that I was interested in star formation histories. So basically, I want to compute the star formation histories of the building blocks as well. Ideally, what we need to do is to go to 6D samples, because those samples will be clean and will be pure with no contamination. The problem is that to get the star formation history of a 6D sample, we need to simulate the selection effects. And when we go to 6D, because of the limited number of stars that we have, also the stars that end up being part of Helmi or Sequoia or Gaia Enceladus is quite limited. So we need more stars and we need to understand better selection effects and all these kind of things. So we decided to use a trick using mixing dynamics and mixing 5D information as well, which is go to pseudo velocity space. The idea is that here you have in velocity space, V phi and Vz, the distribution of stars in the different groups that we have found. If we assume that radial velocity is 0, suddenly this value is changed. Okay, this is a trick. Okay, the V phi Vz is considering proper motion, considering distance, considering radial velocity. But we can assume, imagine that all the stars have radial velocity of 0. Where would they fall in this pseudo velocity plane? Well, they fall in this configuration. And you can see that the blue stars in the left-hand panel, which are the Helmi streams, fall in the green points in the right-hand panel. This clustering disappears, but some ordering is still there. Some clustering is still there. There are some areas that are dominated by these stars still. So basically, we can play this game in order to have larger samples defined only in 5D without relying on radial velocity, that even though they are not purely accreted systems, they are dominated by stars in these accreted systems. And after doing that, another thing that we did is to assign to all of these stars a radial velocity. And the radial velocity that we assign is the one to the closest star in space. Again, this is just an assumption, something that it's a bit of a trick, but the idea was mainly to clean the sample. Okay. And after doing all this game for the Helmi streams, but also for Gaia Enceladus, Thamnos, and Sequoia, this is what we got. Okay. So for the Helmi streams, if you focus on the top panel, we can see that as we move from left to right, we are improving the volume. We are improving selecting more clear samples that are more dominated by Helmi stream stars. And you can see that little by little this blob is extending in time. Little by little this contribution of stars that are the disk dominated sample is cleaned up a little bit, but the magic comes when we assign to each star the radial velocity of the closest star in space, in which case we clearly clean, because all this is a contribution of the local halo, okay? And then we can remove that local halo, because dynamically speaking, the Helmi streams are more similar to the disk than to the halo, because in fact they are located here. Okay, this is disk-like kinematics. The halo is more like here. Okay, so suddenly we clean it quite a lot, and we find that indeed the progenitor of the Helmi stream was a galaxy with lower metallicity that kept forming stars for longer than the halo of our galaxy, and this clump of stars at around 8 gigayears is telling us that it could be that the merger event happened indeed 8 gigayears ago. And if we repeat this and we play the same game for Gaia Enceladus and for Thamnos, this is what we have. For Gaia Enceladus, we have basically this sequence that is expected. This is the blue sequence, all ages older than 10 gigayears. So basically what I was showing before. But the key comes when we do the same for Thamnos. This left and right are two different selections of Thamnos. You can see that it's clearly contaminated by Gaia Enceladus, but it's more extended towards lower metallicities. In fact, if you subtract one to the other, in red, we highlight the population that is intrinsically characteristic of Thamnos. Of course, this population is not characteristic of Thamnos, but the idea is that given the position of Thamnos here, which is kind of mixing with the disk as well, we have quite a lot of contamination from the disk. So basically, this is a unique signal of the stellar populations of the progenitor of Thamnos. Once again, less metallic than Gaia Enceladus, less metallic than the halo of our galaxy, and in terms of extension, very similar, suggesting that it could be that the merger happened around 10 gigayears ago, as was the case for Gaia Enceladus. We did the same for Sequoia. It's shown here. All this is very preliminary. We are still working on that. And basically, that would be everything that I wanted to tell you about Gaia. And I think that it's about time that I stop talking, right?
Fantastic. Thank you so much, Thomas.
So I'm going to skip the void things. Okay, so if you want you can ask me, but just to leave here is not a summary, it's not a conclusion, it's just I would like just to highlight the importance of studying stellar populations. In my case, we are studying star formation histories, but there is chemistry, there is dynamics, there are so many things that we can study that we are really living a golden era with all these spectroscopic surveys and all these works and projects coming up. So thank you so much. Apologies again that I was 15 minutes late to this talk, but if you have any questions, just let me know.
Entirely my fault, Thomas. Thank you.